All right, so welcome everybody to today's session of the Spectral Geometry in the Clouds seminar. Today, it's my pleasure to introduce Peter Sarnak from Princeton University and the Institute of Advanced Studies, who will speak to us about the gap sets for the spectra of cubic graphs. As usual, if you have any questions, you can either unmute yourself and interrupt to ask them, or you can write them in chat and I will relay them for everybody during the talk. And well, I guess that's it. And the floor is yours, Peter.
Okay, thanks, John. And thank you very much for the invitation to speak in this global spectral geometry in the clouds. Great title for a seminar. Sorry that I haven't been able to attend many of these before, but the timing is not so good for me, but I'm delighted to be here today. Everything I say today is joined with Alicia Kollar, who's a young assistant professor in applied physics at Maryland, and Fan Wei, who's here at Princeton as a postdoc at the Institute and the university. My talk will be about very basic objects. At some point, I'll talk about more advanced objects, but the results, I hope, should be clear, and they are. The problem that I'm going to discuss is somehow been around. I've thought around this problem without realizing it explicitly, and as you'll see, the problem really is just about prescribing the spectra of a cubic finite graph. What could be a more basic problem? All right, so, and please feel free to interrupt. I interrupt, so just unmute yourself and ask questions. I don't read the chat. All right, and I'll use this cursor to point, so I'm technologically a little challenged, let's put it that way. All right, so to be clear what I'm talking about, everything X here will be the set of finite connected, it's very important they're connected, 3 regular graphs. So there's an example here of such a graph. I'll be interested in these graphs when their cardinality with the number of vertices gets large. All the effects that will be of interest are when the graph size goes to infinity. So a more complicated example is this one over here. It's a 3 regular Ra-manujan graph. I'll define that in a second, on 16 vertices. So what's our problem? Our problem is to understand the spectra of these. So if you give me any 3 regular graph, y in my set X, the spectrum of y is the usual spectrum of nothing fancier than the adjacency matrix, or I like to call it the Laplacian. It's not an averaging operator, the way I normalize it. So the adjacency operator applied to f is a function on the vertices, is a sum over all y's, all vertices which are adjacent to x of f of y. Since we 3 regular, if f is constant, I will get 3 times the constant if I apply a to the constant. And the eigen 3 is an eigenvalue. It's a simple eigenvalue because I assume that the graphs are connected. And it's a simple exercise that -3 is an eigenvalue of y of the 3 regular graph, if and only if the graph is bipartite. That is, it can be partitioned into 2 equal subsets and all the edges run between the sets and not within the sets. So these are very easy remarks. And then I want to understand, or we want to understand, what can the spectrum look like? It lies between -3 and 3, trivially. And how can you prescribe the spectrum where it may lie if y gets large? So what gaps can be created? This problem arises all over the show. Let me mention a few places. The most celebrated gap is at the top. So a gap between 3 and something less than 3. So a family of graphs is called an expander, say 3 regular graph, if 3 is isolated in the sense that there's a gap at 3. And it goes back to Alon and Bopana early on in the theory when expanders sort of became very popular in the 70s and 80s. who showed that the maximal possible gap, so if you have a sequence of 3 regular graphs whose size gets larger and larger, the interval 2 root 2 to 3 is the maximal possible gap that you could possibly create. They didn't know how to create such a gap with a sequence of graphs. And this was created by Lubotsky, Phillips, and myself, and independently Margulis in 86, 87, showing that 2 root 2, 3, so this gap at the top is optimal and can be achieved. And the proofs at that point were quite sophisticated. They used the Ra-manujan conjectures, the proof of the Ra-manujan conjectures by Eichler, modular forms, and Jacques Langland's correspondence. It was quite involved, and I think people who are most interested in this, such as computer scientists, so you see here that these highly connected sparse graphs are very useful all over in computer science. They're known as expanders. These are optimal expanders, and there's a beautiful survey paper of Huri, Liniel, and Vigdison about expanders where you can see how they're used in many, many different contexts. I used to give lectures saying, well, this is a deep fact and nobody will ever, you should never say that, but I would say it anyway. Nobody will ever give a construction of Ra-manujan graphs without using number theory. As I say, I didn't emphasize enough that I mentioned Eichler. Another key ingredient in the proof that of this Ra-manujan conjecture as it's used to prove this big gap, this optimal gap, is the Riemann hypothesis for curves over finite fields. So if somebody were to do this by hand, I would say anyway, I would say that probably you can't do this without the theory of numbers. Well, I was wrong. Much more recently, Marcus Spielman and Srivastava gave a construction, beautiful construction using interlacing polynomials. And the other key ingredient they used was the theorem of Li and Yang in statistical physics, which puts the eigenvalues of certain partition functions on a circle, just like the Riemann hypothesis puts eigenvalues of Frobenius on a circle. And so the replacement of the Riemann hypothesis is this Li-Yang theorem. The construction is entirely different, and it actually provides you with, solves a beautiful problem they solved. The construction using number theory only allows you to construct these Ra-manujan graphs with this optimal gap if the degree of regularity, in this case that I'm interested in this lecture, is 3, if that number is a prime power plus 1, because a finite field enters decisively. So they actually can construct Ra-manujan graphs with any degree, but their graphs are not explicit, so it's not that, and there will be other features that you'll see where they have not been able to match the number theory. All right, so the gap at the top is the one that many of us know. There's a gap at the bottom that's very interesting. I want to go over it as well. So it arises, and this is how I got involved in this with Alicia Kollar and her co-workers. They were looking at some waveguides and 3 regular layouts in the plane, constructing certain resonant devices. And for that, using the tight binding model for, so this is Schrödinger operators in the 1 electron model in solid state physics. There's a tight binding model, which becomes combinatorial in its limit. And then the question of a gap at the bottom of the spectrum for our 3 regular graph became important. And I want to explain that that was understood beautifully by works of certain people that I'll show in a minute. And 3 regular graphs also come up in carbon clusters, Fullerenes as they're called. These are 3 regular graphs in which are planar and which have the 6 or 5 faces in the planar realization called Fullerenes, and I'll return to that. And in that case, the gap at 0 is important. In fact, the midpoint of where the eigenvalues in what's called the Huckel model in chemistry is the gap between, as I say, in the middle is the decisive one. So these come up in a number of contexts and probably many more. And so let me discuss the one at the bottom because it's very beautiful and it seems to be not as well known as it should be. So there is a gap at the bottom and it's very well understood. If I take any graph Z, finite graph, everything's finite. So if I take any finite graph Z, I'm always assuming it's connected, I can form its line graph. That means it's kind of its dual graph, where the vertices of the line graph are the edges of Z, and you join two of these vertices if they share a common vertex. And because the Laplacian of the adjacent incidence matrix, which is related to the Laplacian, you can look at this matrix or its transpose, and it's a very easy exercise that the spectrum of the line graph of any graph consists of -2 to a certain multiplicity. So -2 is always an eigenvalue with multiplicity m minus n, where m is the number of edges of Z and n is the number of vertices. Union the spectrum of minus twice the identity plus the adjacency of Z. This is even if Z is not regular. This is a general statement. Plus the diagonal matrix, which has multiplicity on the diagonal, the number of the degree of each vertex. So this operator here, this matrix here, has spectrum starting at -2 because A plus D is always non-negative. So the spectrum of the line graph of any graph is always contained in -2. I mean, it won't go very far, but it's never less than -2. So the minimum eigenvalue is greater or equal to -2, and let's call a finite graph whose smallest eigenvalue for its adjacency of the line, so adjacency is -2, a Hofmann graph, because he studied these and he made some really key insights. So the smallest eigenvalue, if I look at it in terms of the Rayleigh quotient, is this infimum, as you all know. And hence, if you take a induced subgraph B of my graph Z, and suppose that my graph's a Hofmann graph in the sense that the smallest eigenvalue is -2, then just from that Rayleigh quotient, the smallest eigenvalue of Z, which is greater or equal to -2, is less than or equal to the minimum, the smallest eigenvalue of B. So if there are induced subgraphs which have an eigenvalue which is less than -2, they are not permissible. So this means that if you have a Hofmann graph, it cannot contain a host, because you can just go look at many small induced subgraphs. They can't be there, because otherwise there'd be an eigenvalue less than -2. So there are theorems that mainly Seymour and Robertson, which tell you that if you have families of graphs which omit certain induced subgraphs, they're forbidden, then often you can classify those graphs. And in this case, this was classified in an absolutely beautiful paper by Cameron, Goethals, Seidel, and Schult in 1975 called Line Graphs, Root Systems, and Elliptic Geometry. And they actually show that except for a finite list of sporadic graphs, all graphs which are Hofmann graphs must be generalized line graphs of the type, slight generalization of the line graph that I've defined. So what they're really saying is that the only way that you can have all the eigenvalues greater or equal to -2, except for a sporadic list, finite list, is that those graphs must be themselves line graphs. The sporadic ones are contained in the root lattice of E8. That's where this elliptic root systems comes in. It's quite a beautiful paper. Anyway, if you use that, you can show the following. So one way to make, remember, X is our 3 regular graphs. I'm back to my 3 regular graphs, capital X. And let me define a map from X to X, which will be very important throughout this lecture. So let me be clear what it is. I call it triangle sewing in map. I start off with the graph Y. I subdivide it, so I take each edge and I put a new vertex in the middle of that edge. And then I take the line graph of the subdivision graph, and you'll get a graph which is 3 times bigger than what you started off with. If your graph Y to begin with was 3 regular, after the subdivision it's 2, 3 biregular. And if you take the line graph of a 2, 3 biregular graph, you get a 3 regular graph. So this map T takes me, which is basically sews in a triangle into each vertex, takes me from the set of 3 regular graphs to the 3 regular graphs, increases the graph 3 times bigger than what it was before. And the spectrum of the new graph is very explicitly related to the spectrum of the old graph through rational dynamics that I'll return to in a minute. But because it's a line graph of something, the smallest eigenvalue must be -2. So in particular, if you want to make a large three regular graph and have no eigenvalues between -3 and -2, so you want to make a gap at the bottom, you just take this map T. And this remarkable theorem of Cameron et al. Allows us, so this was done in a paper of Kollar, myself, and her co-workers, where we were looking at this tight binding Hamiltonian, where I told you that we needed to understand the gap at the bottom. We use that to show, and this will be important, that if you have a sufficiently large graph Y, who's got it has a gap at the bottom between -3 and -2. So if it's gapped at the bottom, then it must be of the form T. It's in the image of T for some Z. So the only way you can create the gap at the bottom is if you the line graph through that construction I gave. So not only does this tell you that -3, -2 is a maximal gap interval, because -2 will always be an eigenvalue of T of something. It tells you the analog of Alon Bopana at the top. Alon Bopana at the top defined the Ra-manujan graph. This defines what I'll call this Hoffman graph, and the Hoffman graphs are all T of something through the construction I gave before. So the biggest gap you can have at the top, we know, and the biggest gap you can have at the bottom is this interval -3, -2. Well, if you have these two understandings at both edges, and if the chemistry, the Fullerene, wants you to understand what other spectra near the middle you can create gaps, let's make a definition. So a closed subset of -3, 3 is a spectral set. So I repeat, everything here is only with graphs that get large. The spectral set, if there's an infinite sequence of 3 regular connected graphs whose spectrum is contained in that set. The complement is a gap set. So that would be, there's an infinite sequence of graphs which have none of their open set as part of their spectrum. And the problem of prescribing, this inverse problem of prescribing the spectrum of 3 regular graphs, are to understand what spectral sets can you create? In particular, what minimal spectral sets can you create, and what maximal gap sets, complements, can you create? And that's what I want to address. And we understand it at the top and the bottom from what I've said. And we want to understand it throughout the spectrum. And it turns out that this problem is extremely rich. I'll give you some answers, but it's clear that the complete answer seems very difficult and very interesting. Now, this problem just with 3 regular graphs, I want to put it in the context of some other problems. And this slide and the next slide will be a little more sophisticated than just 3 regular graphs. So what the problem really, where's this lying? It's a problem about having locally homogeneous geometries. That's what a 3 regular or any regular graph would be. It's locally homogeneous, but globally you glue it in some way. It's finite. And you want to look at local homogeneous geometries in their spectra. Maybe they're Laplacians or other invariant differential operators that might come with it in the continuous case, or in the p-adic world, it's other operators called Hecke operators. In any event, you have these local geometries and they're finite, but you let their volume grow to infinity and you ask what gaps you can create in the spectrum. So for example, if you have a sphere, there's not much to say. You can just make the sphere get large and then the spectrum just becomes dense of the ordinary Laplacian. So no gaps form, very rigid. If you have flat tori, you can degenerate in sort of ways in the fundamental domain of the modular group, as you all know. But if you look at the spectrum, because you have to have it has to become short in one side, you again can't create gaps. In the case of hyperbolic surfaces, which is sort of the analog of cubic graphs, so you're taking the upper half plane divided by a lattice, giving you a hyperbolic surface, say a smooth hyperbolic surface of some genus, and you want the volume to go to infinity, so the genus gets large. So I've drawn a picture here of what that hyperbolic surface looks like. By the way, is there anybody there? I assume so. I was sort of just talking to myself.
Yes.
Okay, good.
No, it's quite clear up till now.
Okay, I've made the mistake once of giving my class in the spring and having everybody in the waiting room and just speaking to myself for an hour. So please interrupt. Yeah. So here you see a hyperbolic surface. The genus gets large. Whether that you can create a gap between in the Laplacian in the interval 0 to a quarter is a famous. We don't know whether you can create that larger gap. There's a conjecture of Selberg which says that for congruence groups that's true. So the gap at the bottom, which is very much the analog of the Lon-Bopana gap at the top, has been studied. This, of course, the Selberg conjecture is something that anybody close to me has studied over the years. But we don't know what happens above a quarter. What gaps can you create by arbitrary high genus Riemann surfaces compact above a quarter? And that's exactly the question I'm asking for graphs here. And based on what we do here, I can guess some answers, but somehow we haven't asked this question. It's been sitting there waiting to be asked.
I have a little question while we're talking. In your previous slide, it's not quite consistent between spheres and hyperbolic surfaces, because for your spheres, you're allowing the radius to vary, the curvature to vary, and not in the bottom.
Correct.
You wouldn't get this effect if you fix the sectional curvature.
Right. I was just trying to give a few examples where no gaps create. The most interesting is the hyperbolic surfaces. Yeah.
Peter, and there were some results about sequences of surfaces which sort of converge to the hyperbolic surfaces which converge to the universal cover, and then given any interval above 1 quarter,
this is yeah, I'm going to get to this right now. Yeah. So the point is, to make interesting gaps, you can't converge Bignamini-Schramm to the universal cover, because that will not allow gaps, right?
Okay. So you have to converge to something else. And for infinite area, you would, is it interesting to look at resonances, because like the largest strip and so on?
Absolutely. But it's already sufficiently complicated with 3 regular graphs. Let me point out, however, that if you go to higher rank, there's a remarkable feature that you can't ever create gaps. So suppose I have a higher rank symmetric space, or if it were the combinatorial analog of Ra-manujan buildings. So this, by the way, is the next 2 slides are fancy material. Ignore it. I'll come back to 3 regular graphs if you don't like this. But there's this remarkable theorem of the 7 samurai, as they call themselves, Bergeron, etc., which is a remarkable rigidity theorem, that if you are in a higher rank situation and you take a quotient, so S is a higher rank Riemannian symmetric space, you take a quotient of that, compact quotient of this Riemannian symmetric space, and it's got some volume, and you let the volume go to infinity, then no matter how you try, or how you try, whatever you do, this sequence, once the volume goes to infinity, must Bignamini-Schramm converge to the universal cover. That is to say that as the volume gets larger, if you take a random point inside the surface, it's not true that the injectivity radius could remain fixed, but there will be, most points will have larger and larger injectivity radius. So more, if you look at a typical point in the neighborhood of that point, you will look more and more like a universal cover. And then it's a soft theorem from there. So this is a deep theorem. This is it comes from a lot of rigidity of higher rank lattices. But in particular, the spectrum, at least the tempered part, just ignore what that means, must converge to the Plancherel measure, and no gaps can be created. So in higher rank, you can't play this game of creating any interesting gaps. So it would be the analog in the 3 regular graph that you have to fill out the spectrum -3 and 3, which we've seen, well, sorry, except for the top gap, so that there's a word tempered there. But this is a very rigid situation. There's another situation that Serre is still active. He's 90 something. 2 years ago, he wrote a beautiful paper, and it'll be relevant in my talk, proved the following. So suppose you look, so this is an eigenvalue problem, which is coming from algebraic geometry. You're looking at a curve over a finite field FQ. So Q is fixed, you have a finite field FQ, and you look at a curve, a connected curve over FQ of large genus, or you look at an abelian variety of large dimension over this finite field FQ. Q is fixed. Now, there's an operator called Frobenius on the cohomology, which is known to have the property that all its eigenvalues are of modulus square root q. That's for abelian varieties, is a theorem basically of Hasse, excuse me, and for curves. So the eigenvalues, also because I'm looking at a curve or an abelian variety, the eigenvalues will be on the circle radius root q, and they'll be symmetrically replaced. The characteristic polynomial is palindromic. It reads forwards and backwards the same way. So if the curves of genus G, there are two G eigenvalues placed symmetrically on the circle, and you can ask, can you create gaps in the spectrum? Could you take a sequence of curves of larger and larger genus? Where can these eigenvalues concentrate? There's a beautiful theorem of Fassmann and Vladut that goes back to Gopa codes in their analysis of Gopa codes, which show that you cannot create any gaps as the genus goes to infinity. The spectrum has to become dense in the circle. On the other hand, what Sarah showed recently is that for abelian varieties over FQ, there is only one obstruction as to what you can do, and that is that you can arrange the eigenvalues to sit in a closed subset K as long as it's large in the sense that its transfinite diameter is at least q to the quarter. I'll define transfinite diameter in a second, but for a circle of radius root q, the transfinite diameter is root q, or the capacity, same thing. And what he's saying is that the set can't be too small. It has to have transfinite diameter at least q to the quarter. And if so, then you can construct a sequence of abelian varieties with the spectrum sticking into this weird set. I'll explain what transfinite diameter is now, but what you should take away from this is curves are very rigid. They can't create gaps. A higher rank from the previous slide is very rigid, but abelian varieties, there's sufficiently many of them that you can create quite a lot, but there's one restriction. All right, so what's this transfinite diameter? There's an absolutely beautiful theorem of Fecatos from 1930, extended by Tsego and Polya and Rumley and many others in higher dimensions, but it is a quite stunning theorem and will be very relevant to us. Suppose I have a compact subset of the plane. Its capacity or transfinite diameter, I think Fecatos talks about transfinite diameter as defined here, and that has been shown to be equal to the capacity by potential theorists like Alfors. But here's his theorem. Well, let me first define the transfinite diameter. So if I have my compact set K, I take n points in the set, and I form the geometric mean, the biggest geometric mean I can create by putting n points in the set. So dn is the maximum of this geometric mean of placing n points in the set. It's easy to see that dn is decreasing as you increase n, and it decreases to a number, and that's called the transfinite diameter of your compact set K. So what Fecatos' theorem says is that suppose I have a set K whose transfinite diameter is less than 1, and suppose it contains algebraic integers, all of whose Galois conjugates, they satisfy the same polynomial equation, all of those Galois conjugates also lie in K. Then if the set has capacity or transfinite diameter less than 1, then that set must be finite. So you have, if you're going to have infinitely many algebraic integers and all their Galois conjugates contained in the set K, it must have capacity at least 1. And you can imagine how that's proved, because if this is sharp, if you have the roots of unity, they lie in the circle, and the transfinite diameter is 1. And the conjugates of roots of unity are roots of unity. But otherwise, it's a very beautiful and deep theorem. And this will play a big role. It plays obviously a role in Sarah's theorem that you just saw, and it'll play a role in what I'm about to say. All right. So,
and since this is about complex numbers, it applies to chromatic polynomials as well. So if you want to get gaps between like chromatic roots and stuff, then this could also play a role, right?
Yeah, absolutely. So what's going to be relevant for us, as you can imagine, is that if you have the characteristic polynomial of the adjacency matrix of a graph, the roots are algebraic integers, clearly, because the matrix, the characteristic polynomial starts off with x to the n, and otherwise is integers. And because the matrix is symmetric diagonalizable, all the eigenvalues are also, all the other eigenvalues are also roots, and they're all real. And so the capacity, you would imagine that from this theorem, and it's not a difficult deduction, that'll be one of the things I'll deduce, that any spectral set for a 3 regular graph must have capacity greater than or equal to 1. And incredibly, you're going to see that sharp. Incredibly that sharp.
But for directed graphs, you could in principle can have complex eigenvalues, right?
Yeah, this theorem is about complex as well, but the point is I'm going to be using it in the real. Yeah,
of course.
Okay. So now back to 3 regular graphs, and now everything I say is joined with Alicia Kollar, except at the end, which is also joined with Fan Wei. So the moral of this lecture is that 3 regular graphs are incredibly rich, showing both fluid and rigid features, and I'm going to show you how these things rigidify as you put conditions on the graph. So the first thing we wanted to understand was, is it possible to make a gap at any point? So we've seen the gap at the top, we've seen the gap at the bottom, but could you make a gap in the middle? Can you construct a sequence of 3 regular graphs which have a gap at any point? So is it true that for every c in -3, it is true, that's theorem 1. Is it true that for every point in -3, 3, you can't, the 3 is always an eigenvalue. -3 need not be, so I'm using -3. The topological space is the interval -3, 3 with the usual topology, so that's an open set. So is it true that for every point c, can you find an infinite sequence of graphs, and we're even going to show that you can make them planar, such that there's a neighborhood of c, and none of the graphs have eigenvalues in that neighborhood? This is quite tricky. So that's our first theorem. That shows the very different feature to the rigidity features I was pointing out, is you can create gaps at any point, and even using planar graphs. Remember, I didn't explain this, but the expander graphs cannot be planar, because planar graphs by a min-cut theorem, there's a well-known min-cut theorem, probably the sharpest version due to Lipton and Tarjan, says that if you have a sequence of planar graphs whose size goes to infinity, then you can't gap the point 3. Say I'm talking about 3 regular graphs. So this is quite subtle, especially at the top. And then the second theorem, in order to show you the structure of what spectral sets can look like, is that there is some general lower bounds which are remarkably sharp. This is one of the things we really enjoyed. So the first lower bound, which you imagine, and correctly if you're imagining that follows from Fecatos quite easily, the capacity of any spectral set. So remember, a spectral set is a set for which there's an infinite sequence of 3 regular graphs whose spectrum all are contained in K. So it cannot be too small. It cannot be a finite set. It has to have at least some serious capacity. The capacity has to be at least 1, and you'll see that sharp. And then a second theorem, which is quite a bit more difficult to prove because it doesn't involve this use of any easy thing. It's a combinatorial theorem, that any spectral set must meet any interval in -3, 3. If you give me any interval whose length is bigger than 2, and you'll see this is sharp 2, then that interval must intersect K. You cannot make any interval length bigger than 2 free of eigenvalues of 3 regular graphs. Just not possible. And to show you that sharp, this is one of our main theorems, and I'm going to give you an example of this. So there's an interval of length 2, -1, 1. There's an infinite sequence of planar graphs which has no eigenvalues in -1, 1. And the only other such interval we know is -2, 0. There's an infinite sequence of graphs. We don't know that they can be made planar, such that -2, 0 is free of eigenvalues. And not only is that the statement that the length of the interval is 2 is maximal. So these are maximal gapped intervals inside -3, 3. So we had discussed the gap at the top, the gap at the bottom. Those are understood. And these are two new maximal gapped intervals. All this is described in a preprint that we posted recently, Alicia, Kollar, and myself. Let me show you the graphs at least. So here's a gap -1, 1, and planar. So there's a 3 regular graph. I think you can see it's constructed by some kind of periodicity. Of course, it's got a periodicity, except for the ends, which are not periodic. They're capped in some carefully engineered way. So these are 3 regular. You can see them. I can make more and more layers in the middle to make it larger and larger. And if you numerically compute the eigenvalues, you never get anything between -1 and 1. You actually have eigenvalues at 1 and -1 with high multiplicity. And then the eigenvalues go up to 3 and -3, and they become dense outside the interval -1, 1. This is one example we have. We don't have many examples, but this is one example. And this numerics, of course, we have a complete proof that there are no eigenvalues in the interval. So -1, 1 is, and this graph is planar. It took us a long time to, we didn't realize it was planar for the longest time, because it was when we first found it, it was looking things like this. The other graph is almost planar, which makes an interval -2, 2, as you can see here. I'll say at the end a word of how we found these. We found this using Bloch wave theory, and my co-worker Alicia Kollar is an absolute expert at all solid state physicists know everything about Bloch wave theory, and that's how we found these, using periodic covers. All right, I want to get back to this capacity because there's something quite beautiful going on here. So as I said, if you take the line graph, so suppose you take that map T, that triangle sewing in map, T of Y. So the spectrum of T of Y actually can be computed explicitly. This is just an exercise in linear algebra. It is the inverse image with multiplicities of the spectrum of Y, union -2 to multiplicity n over 2. So if I start off with Y, which has the number of vertices is n, and I apply T to it, which now has 3 times more vertices and 3 times more eigenvalues, then the new eigenvalues are going to be add the number -2, add the number 0 to the multiplicity n over 2 each, and then add the numbers which are F inverse, where F is this quadratic polynomial, evaluated at the spectrum of sigma of Y. This is basically exercises, as I said, in linear algebra. So we have an exact formula if we understand the dynamics of F. And our proofs of the theorem say, for example, that you can find a gap at every point, makes very heavy use of the rational dynamics of this map F, which corresponds on the spectral side to the map T, which is operating on the graphs. So if you look at F as a map from R into R, it's basically got this Kanto set, on which it acts very chaotically, and then outside of that, it wanders off to infinity. So if you take the map F, as it's described here, and you look at the inverse image of -3, 3, you'll get F is 2 to 1, you'll get these 2 intervals. And so -3, 3 will contain F inverse of -3, 3. And then if you apply F -2, that will cut that up further into what starts to look like a Kanto set. So if I take lambda, the intersection of F to the m of -3 and 3, you get a set, a Kanto-like set, whose dimension I thought I had to compute to understand something, but that was quickly abandoned when the much more important quantity for this Kanto set is its capacity. So you get a Kanto set, and notice that I'm throwing in the point 0 and -2 on each iteration. So I'm going to define a very, okay, here's the dynamics. Just let me explain the dynamics of F. So this intersection set here, sorry, this set lambda is exactly the set which does not go to infinity under iterates of F. And the restriction of F to lambda is a shift. It's a Bernoulli shift. It's completely chaotic. And outside any point which is not in this Kanto set, as you see here, if I start with any point, it'll go out to infinity. So the Kanto set here is a set which is this closed set. It's often called the Julia set. This is a very simple example. I think it's called the Julia. I forget which is the Fatou set and which is the Julia set. I think it's called the Julia set. It's this closed set on which the restriction of F to that dynamics is just a shift. And the fact that it's a shift and complicated is used in our proof. All right, so we have this topology, this set lambda, which is contained in -3, 3. And if you restrict f to lambda, I just said that it's the equivalent to a shift on the symbols -0, 1 to the integers. It turns out that the inverse image of 0, which is that what in the formula for the new eigenvalues from the old eigenvalues, this set of points will accumulate on lambda. So this is a discrete set. This union m equals 0 to infinity of fm of 0 is a discrete set whose accumulation points are exactly lambda. So there's a very important set A here, which consists of this Kanto set lambda union this discrete set. Each point is isolated, but those points condense onto lambda. So A is a closed set. And this set is a fundamental set, which you could imagine is relevant for us. And here's our big fact about A. A is a spectral set. In other words, because if I start off with one of these 3 regular graphs and apply T repeatedly, it won't get, all the eigenvalues are contained in A. Quite incredibly, the capacity or the transfinite diameter of A is exactly 1, showing that that lower bound is sharp. And if you have, this uses the full force of that theorem of Cameron. If you have a point y in x and whose spectrum is contained in A, so we're saying that there's an infinite sequence of 3 regular graphs whose spectra are all contained in A, the claim is that there are only finitely many orbits, T orbits, so their infinite sequence is always constructed by applying T to a finite set of Ys. There are only finitely many such orbits. We don't know all the orbits, we know at least 2 orbits. But in any event, A is this remarkable set showing that it's kind of the most Swiss cheese kind of set, which it's as small of capacity that any spectral set can have. So let me summarize what we have at this point. In terms of maximal gap intervals and minimal spectral sets, which are just the complement. So maximal gap intervals, I've already explained Allon-Bopana. There's also -3, -2, that was the Hoffman graphs. And then our new ones, which are length 2 and are maximal gap sets. I don't know any other explicit ones. Of course, by Zorn's lemma, you can put anything in a maximal one, and we don't know how to determine those, but these are the basic building blocks. And then minimal spectral sets, which are not intervals. We have A, the set A that I just described, which has got capacity equal to 1 and is minimal. We have a proof that it's minimal, not just that the capacity can't be smaller, but you cannot have a smaller closed set, which is spectral for an infinite sequence of 3 regular graphs. And then there's a slight improvement here of and this is very important. I want to explain a theorem which I really love and is not well known too. So I want to explain that. And that is that the following set, so remember this 2√2,3, that gap, the Allon-Bopana gap, is an optimal interval gap. But this set is a spectral set, -2√2, 2√2 union 3. In other words, the Ra-manujan graphs, which are not bipartite. So I want to, the construction of Ra-manujan graphs by Srivastava, it's Spielmann et al. That construction, which I mentioned earlier, only works, and nobody's ever been able to fix up this lacuna, only works for bipartite. So they don't know how to make a non-bipartite Ra-manujan graph, which would be something whose spectrum lies between -2√2 +2√2, and of course always has 3 as an eigenvalue. But number theory provides these. And so there is an infinite sequence of Ra-manujan graphs whose spectrum is, so K is a spectral set, but actually you cannot make more gaps. This is actually a minimal spectral set. And that's a very deep theorem that I want to explain in a second. All right, so the minimum, I've explained the minimal capacity, and this discussion that this set here, this one here is a minimal spectral, is a beautiful theorem of Hebert, Glasser, and V. Rugg. So I mentioned the 7 authors that in higher rank, you can never create gaps. These three authors, one of them is this common to the 7 and this 3, maybe 2, is the following remarkable theorem. Suppose I give you a sequence of Ra-manujan graphs. So these are a sequence of 3 regular graphs whose spectrum are contained in this set here, K1, the first set, minus 2 root 2, 2 root 2, union 3. Then that sequence of graphs must Binyamini-Schramm converge to the 3 regular tree. That's a deep theorem. Now, there are people who mix this up, including me, including Sarah, that if the girth of the graphs gets large, it's very easy to see that you can't make any other gaps that you Binyamini-Schramm converge to the tree, because if the girth gets large, you are saying that locally you look like the tree everywhere. And they're saying that just because you've restricted the spectrum, you have to Binyamini-Schramm. You don't have to converge locally. There may be many points where you don't look like the tree, but for most points, you have to look like the 3 regular tree. And the minute you look like the 3 regular tree, then the spectral measures must converge. So this set here is actually a minimal spectral set, just like our set capital A is a minimal spectral set. So that's sort of what we know in terms of what you can create in the middle and in terms of this remarkable set which has a minimal transfinite diameter. What's going on there? All right. All right, so I want to spend the next 10 minutes explaining what we have done with Van Wey, and that is if you put restrictions on the graph, and this is very important in applications. Maybe you want your graphs to be planar. Maybe you want some other conditions on the graph. Can you still create these gaps, these interesting structured spectral sets? So gaps are usually what you're trying to create. And the answer is, how do they rigidify? So firstly, if you just put the planar condition, they don't rigidify. The main theorem was you can create gaps anyway. But suppose you planar, and in your planar realization, and there's only one planar topological realization for these things, once we planar, we can talk about the sides of the faces. So now the graph has got these vertices, edges, and faces because we have planar graph. And suppose I limit the number of sides to a face. So I'll define F3M to be the planar graphs, which are 3 regular, which have at most M faces. In the case of 6 faces is going to be 6 sides to a face. At most 6 sides to a face is going to be very important. A Fullerene, by definition, is exactly the subset of these F3-6s, which have only 6 faces or 5, hexagons and pentagons. So they are more restricted. And so the question is, if I have F3-6 or Fullerenes or F3Ms or FRNs defined in the obvious way, what can I create? Or does the thing rigidify? And the answer is quite beautiful. Here are Fullerenes. Turns out from the Euler formula that if you have a Fullerene that you only have hexagons and pentagons, they have to be exactly 12 pentagons. And you can see them in these pictures. These are graphs of Fullerenes drawn on a surface. So they're purple there, or the blue there is, in these cases, the hexagons. And otherwise, when you get large, you'll have mainly hexagon. The blue is the pentagon, and there'll be mainly hexagons. This thing's called a nanotube, which will play a role in a minute. Okay, so those are examples of Fullerenes. And the question is, what gaps can you create in the spectrum of the adjacency matrix of this problem that's fundamental? Okay, and this is what we can prove. This is being written up. So for F3-6, so for planar graphs, 3 regular with at most 6 sides per face, there is a unique maximal gap set, -1, 1. In fact, you saw that example that I drew happened to have at most 6 sides per face. It had a lot of hexagons. If you look, if I go back to it, as you can see, in the middle there, it's got some triangles. So this is not a Fullerene, and that becomes a trickier question. So there's a unique maximum. Things become very rigid. The only gap you can create is -1, 1. That's the biggest gap you can create. The spectrum has to become dense between -3 and -1 and 1 and 3 if the number of vertices goes to infinity. So we've completely rigidified except for this interval. For Fullerenes, we can't make as big a gap as that. There's a unique number there. These are algebraic numbers. I've written them to some number of decimal places. The interval is smaller than -1, 1. It's -3.82 plus 3.82 with a unique point eigenvalue in the middle there. That's what it's converging to. And it's the complete answer for Fullerenes. This is the unique maximal gap set, and you have to become dense outside. And in terms of when do you rigidify, we believe that the minute you put 7 here instead of 6, you probably can then create gaps everywhere. But right now we only have a proof that if you allow 64 sides to a face, then you'll rigidify. All right, so I think I've stated all the theorems I wanted to state. They're all about prescribing the spectra and how you rigidify as you put conditions on the graphs. Everything was 3 regular graphs. So let me say a few words about the proofs. Firstly, the fact that you can make a gap at any point makes use of that map T heavily, and the dynamics of the rational map plays a critical role. I gave this lecture a month or 2 ago, and Will Savin, who was in the audience, came back the next day with a generalization of T, some other sewing in graphs for which he could compute the new spectra from the old in terms of more complicated dynamics. I don't know what kind of rational dynamical maps come from this, can be created this way. For us, but as a consequence, in particular, he has a new spectral set, which is not our spectral set, which has capacity 1 also, achieves the minimum bound for the capacity. Shows you that the sets which are spectral sets of minimal capacity are probably very complicated and not that easy to describe. But nevertheless, he's found a new one. I mentioned this. How do we find that example I gave you? So how do you find, you clearly, as Dima said, and this is absolutely correct, if you Binyamini-Schramm converge to the 3 regular tree, you'll never create gaps. Or in a hyperbolic geometry setting, if you have a sequence of hyperbolic surfaces whose genus goes to infinity and which Binyamini-Schramm converge to the hyperbolic plane, you'll get the spectrum will become dense in a quarter infinity. So you have to find some very cunning other limits. So you want a Binyamini-Schramm, so to speak, converge to something else. And we found all these as Z2 or Z covers using Bloch wave theory by experimenting with many small graphs and found many examples with gaps until we found this maximal gap and then proved that it's maximal. So somehow matching the gap we could create with what we could prove combinatorially cannot be bigger was quite pleasing. So I want to emphasize that all our graphs that we are creating are coming from abelian covers. So the beauty of Bloch wave theory is it allows you to study the universal abelian cover and also finite abelian covers in terms of bands and gaps, which you can compute explicitly in any given example. And the point is here that we're engineering such examples with maximal gaps. So there's no doubt you could use this also in the hyperbolic setting to create some gaps in a quarter infinity. I've never seen it done, but whether you can create a gap high up in the spectrum is probably problematic. In fact, if you think of Schrodinger operators with potential, as everybody knows, there's a standard feature that in 1 dimension, all gaps can be open. So for the Hills equation, but the minute you go to 2 and higher dimensions, then eventually the gaps must all close. So just to emphasize, all our interesting examples that were created in the middle are created by Bloch wave theory. And of course, the set A by the map T. And yeah, what else do I need to say? The maximality of the gap set, which is like the Alon-Bopana theorem, that is to say that if you have any sequence of graphs, you must have an eigenvalue in some interval. That's pure combinatorics. So we have combinatorial proofs of those. That's straight combinatorics. So I think I've explained in very vague terms what goes into the proofs. I think I'm running out of time. I have some examples of abelian covers, but maybe this may be a good place stop. And if I say anything that you should take away from this is that three regular graphs are incredibly rich. Prescribing their spectrum is quite a rich and complicated problem, unlike the case of abelian varieties. And the capacity is a very important thing to measure the size of these sets because of Fecatos theorem. Thank you.
Thanks a lot for this talk. Does anybody have questions for the speaker? Can you ask them? Okay, go on, Dima.
I have a comment that there are some results about some spectral Laplacians on fractals, which look very much like this triangle insertion map. That there is some sort of polynomial, and then there is some counter set.
Okay, right. So there is the Henon towers map. There's a spectrum of a graph there, which is computed in a very similar fashion by such iterations of f's, and they're more complicated versions. So there are some dynamical systems associated with those too. But so we point this out. That's correct. I don't know about fractal, but this is in terms of this problem. I think it's called the Henon tower problem. Yeah, so it's correct. There's a computation of some variant of this, but as you can see, it's completely natural from this division. The desire to create a new graph from the old graph and create new bigger and bigger gaps.
Yeah. And what can you say for four regular graphs, right? Because you can also...
So a lot of what, I must say that the proofs of the extremality, that is that that the interval of length 2 must, any interval of length bigger than 2 must contain an eigenvalue. There we're using three regular very heavily. So in other words, there are a lot of combinatorial phases that, situations that come up, and we can limit them. And if we had four regular, it just would be kind of frightening to try and understand it. So of course, if you two regular, you're just a cycle. Three regular, you already have hit the most complicated thing, but you still, I mean, if you have a Hamilton cycle, which is what we use a lot in the graph, you can use it to make an eigenfunction. Of course, the way you prove the optimality is to construct an approximate eigenfunction and use Wahl's criteria that just linear algebra, that if you have an approximate eigenfunction, you have an eigenvalue nearby. To do that, you need to entertain any shape, because all you know is that your graph is large. So every question I've asked can be asked for four regular, but some of our proofs at this point are absolutely using three regular, but I don't think in a way that's completely I think eventually someone will be able to get around it, but we are using that there heavily. The issue of the gap at the top and the bottom, that's not so much an issue, because the gap at the top, the Alon-Bopana, is for any R regular graph. The gap at the bottom, the Hoffman thing, is general. -2 is always the number from line graphs. So I haven't quite thought through that carefully, but the problems make sense and should be asked for any geometries. The point here is, I think that hyperbolic surfaces are going to go a little bit like this too. In other words, there's a gap 0 that we don't know how to create, because we don't know how to prove the Ra-manujan conjecture, but we have something very close there. And the interesting thing is there's a very interesting problem. Why does the Srivastava et al. Proof why can't you adapt it to Riemann surfaces? Nobody, and that I think is connected with the fact that they really can only do the bipartite thing. In any event, that remains open. And then the other gaps you can create, I don't know. I think you can certainly create gaps just above a quarter, but when you go high in the spectrum, I think you're going to get the feature that all these bands and gaps the bands want to cover everything. And so there may be a limit. It may, it's completely open. Can you create a gap arbitrarily high? So here's a question. I have a sequence of, is it true that I can create a gap? So you give me a number, a very large number, and I want to create a gap around that number for arbitrary large hyperbolic surfaces, for the Laplacian arbitrary large hyperbolic surfaces. I don't know. You can certainly use abelian covers to do something near a quarter. But that hasn't been done as far as I know.
But you have some very explicit sequences of graphs, so sort of glue a hyperbolic triangle.
Yeah, but that's the graphs don't pick up the high energy eigenvalues, the high oscillating modes, you see.
I see, okay.
I don't know. Yeah. And I don't know how to go, the kind of Brooks, I think what you're thinking of is this Brooks phenomenon.
Exactly, yes.
That's about low eigenvalues. That's eigenvalues near 0 or eigenvalues near 3 for the graph. I think the problems become a little different when you move up away from a quarter up in the spectrum.
Yes.
Yeah. At least that's my intuition. And remember, this rigidity is kind of remarkable too. So, yeah.
Thanks a lot, Dima, for the question. Do we have any other questions?
I have a question. Peter, when you have a three regular graph, like any other regular graph, you can write an exact trace formula. And the element which comes there for the periodic orbits is just the count of the number of periodic orbits without backscatter.
Correct.
Now, when you have in your spectrum such structures as those large gaps, how does it reflect in the counting of periodic orbits?
So the gap at the top is why we want the gap. It's why Selberg made the conjecture. It's why Ra-manujan made the conjecture. It's that if you count the number of periodic orbits, you'll have a main term which comes from the big eigenvalue 3, and then the remainder will be as small as possible. Cannot be smaller because this is exactly because the spectrum, that's what Alon Bopana is saying, but it's anyway obvious in the count. So it's saying that the count for periodic orbits is as sharp as it can be. It shows square root cancellation in the count. In other words, the number of periodic orbits of size length less than x is e to the x plus something which is at most e to the x over 2, basically. And if there's some eigenvalues spread in the interval, then it would come out as an extra term there. The gaps, in terms of periodic orbits, gaps inside the spectrum or the bottom, I don't know in terms of any clean periodic orbit interpretation. So it's at the top, there's an obvious interpretation. It's like the Perron-Frobenius eigenvalues sticking out. But in the middle where people want gaps in terms of, the gap at the bottom measures how far away you are from being bipartite. So somehow there, when you take the line graph of a graph, you're very far from bipartite, because bipartite means you have an eigenvalue -3 and you're making the gap all the way up to -2. So I think probably we could give an interpretation there. The -1 gap that we found by some lovely construction that you saw there, I'm not so sure. In terms of Fullerenes, it's saying that you can, there is a problem with Fullerenes that I don't know the answer to, and it looks like an absolutely beautiful problem. And that is, can you actually create a gap at the middle? Meaning you take the top, so you got a 3 regular Fullerene, you take the top half of the eigenvalues and the bottom half, and you want the gap between the top half, between the middle one, these two middle ones to be as, can you keep that gap open or not when the graph goes to infinity? Seems fundamental problem, and we couldn't answer that so far. Because where we create a gap, as I explained to you, it turns out that in our constructions, the demarcation in the middle is actually is not in the middle of the gap, but it's on one side. so that gap went to 0. And I don't know that it's physically that important, because I don't know how you can make such a carbon cluster with so many pieces. But in Huckel theory, that gap is what measures the stability of the molecule, in this very simple idea in chemistry. But combinatorially, it's a great problem. Can you keep the gap between the two middle ones open for arbitrary large Fullerene? We've been trying to do that and have failed. It's a beautiful problem.
This actually brings up a question that I've been wondering myself during the talk. So you had those gaps at -3 for these line graphs between -3 and -2, say. But would it be possible to have a bipartite graph, so with -3 as an eigenvalue, and then some interval that's able to go up to -2? Or
absolutely. That's the very definition that we gave of a Ra-manujan graph. Is we first say, if it's bipartite, then we demand what you just said.
Okay.
And so the bipartite Ra-manujan graph is exactly the fact that -3 is isolated, because if you bipartite, the spectrum's symmetric. So that's exactly what you say. But if you're not bipartite, you've removed -3, then you demand, all right. So in a way, this paper of, with the elliptic geometry is quite remarkable, because it really tells you how close that gap measures how close you are to bipartite. Yeah. This Cameron paper. Yeah.
Peter, and there was this mysterious number which kind of was sitting in the middle of a spectral gap in one of your theorems.
It is.
What was that number?
Some cosine something coming from Bloch wave theory.
Okay.
We're still ironing that out. There's one point eigenvalue in the infinite. As you can imagine, when you take this limit, it comes from. I'll tell you where it's really coming from. It's coming from a 0.5 nanotube. So it looks something like this. You see this thing at the bottom here? Mm-hmm. The spectrum of this thing here has a gap, and it's got an eigenvalue. One eigenvalue in the middle. The spectrum of this thing here, if it's extended infinitely.
Okay.
When you cap it off with this 6 on each side pentagons, so without the capping off, it's an interval which I wrote down there, and which I can give you the extreme points of that interval was -3.8 plus 3.8. When you cap it off here, which is, you now have an eigenvalue problem where you're making a finite rank perturbation, you introduce a multiplicity 4, the symmetry, one eigenvalue in there. We can prove that, and we know what that number is in closed form. That's what that number is. So it is the Fullerene answer, but it doesn't answer that other more subtle question of whether you can keep the gap between the median, the midpoint, because the midpoint happens not to be in the gap. If it were in the gap, we would be done. So I don't know the answer about Fullerene. Is there a Fullerene? If your Fullerene Binyamini Shram converge to the honeycomb, then of course there's no, the spectrum is -3,3. So the only way you're making a gap is by this kind of gluing here, and that's part of the theorem. It's kind of a beautiful analog of hyperbolic surfaces, but very rigid.
Thanks. Are there any other questions for Peter?
Kind of very idle question. Can you have a continuous analog of a theorem of Hoffman about line graphs? So, suppose something is a unit sphere bundle of something else, then the spectrum is blah, 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 and conversely.
It's a good question. I think that you can, by the way, the Hoffman thing, no, the converse, the one direction is easy. The fact that a line graph has the spectrum -2, or that identity that I wrote down, is the Laplacian, just like all Laplacians, come from lowering and, going up and down, right? Mm-hmm. So if you go up and down, what's called the incidence matrix. That's a not square matrix, which consists of the matrix with zeros, ones, and there's variance with minus ones, which is indexed by the rows and by the columns separately. If you take that matrix and you take its transpose one way and its transpose the other way, you get the two Laplacians of the line graph and of the graph. And that's where this identity comes from, and that's where the -2 comes from. So that feature, of course, you do have in geometry in many places. Even in the Hodge theorem, you go up and down, you have spectrum on Laplacian, and the difference between them is the kernels. And that's the analog of the kernels is this -2 to some multiplicity. So yes, that aspect is general, but the interesting theorem there is this amazing theorem of Cameron et al., which is the converse. And that comes from something that's purely combinatorial as far as I know. So as I explained, where's that coming from? It's conceptually amazing. You immediately see that certain graphs are forbidden, because if there's a graph which has eigenvalue less than -2 for its adjacency, it cannot be an induced subgraph of your large graph. And then there's this amazing theorem of Robinson and Seymour about graph minors, about that you should expect that if you put a lot of conditions about excluding minors, then you should know what you're looking at.
Yeah, so you need some continuous analog of Robertson-Seymour. So,
yeah, so I don't know. Yeah, okay, I don't know.
I see. But that could be tricky.
That's a very combinatorial theorem, probably one of the deepest in combinatorics now. Yeah, the graph minor theorem.
Yeah.
So I think we may have time for one last question if someone has one. All right. Otherwise, thanks a lot for this talk today. I think that it did spring up many new questions, which owes the richness, I guess, of these.
Three regulars rich, yeah.
Yeah. I mean, I think you gave a good
PR for it. Yeah. Okay.
Yeah. No. But yeah, a good example of how rich they are here. We will reconvene next week for the next session of the Spectral Geometry in the Cloud seminar for a talk by Edouard Houdet, who will talk to us about metric optimization in spectral geometry. So for this week, I think we can thank the speaker again and see you all on next week.
Thank you.
Thanks a lot.
Bye. Thank you, Peter.